Hello everyone, we are doing today's section 2.5, series solutions near ordinary point. Let's consider differential equation of a second order, homogeneous, and the coefficients are p of x, dy, second derivative dx plus q of x, dy, dx plus r of x, y equals to 0. Homogeneous equation, p, q, and r are polynomials. For example, let's consider equation looking like this: x squared y second derivative plus x y first derivative, little thing over here, y first derivative plus x minus square minus new square y equals to 0. By the way, this is Bessel's equation. Just example. Just example of second order equation with polynomial coefficients. So here is polynomial of second order, first order, and like a second order polynomial, right? So we are going to call point x equals x0 an ordinary point of the equation if p of x0, the coefficient polynomial of a second derivative, is not equal to 0. Otherwise, we are going to call it singular point. For example, let's look at this equation. Do we have like ordinary points or singular points for this equation? Well, let's look at p. P of x here is x squared. If we set it up to 0, we're going to find that x equals 0 is a singular point, right? All other points x for this equation are ordinary. X not equal to 0, ordinary. Okay, so what we can do for an ordinary point, we can divide our polynomial by p of x. So we can write it down like this: second derivative y plus q divided over p, first derivative y, plus r divided over p, y equals to 0. And rewrite it like in more familiar form for us: second derivative plus p of x. Here, this little p different from the big P which sits over here in the beginning, and q, little q of x, y equals to 0. So my little p is actually the ratio of big Q and big P, and my little q is a ratio of like r and p. And again, they depend on x. They are going to be kind of Russian fractions. Okay, so for now, guys, we are going to work only with ordinary points. And what is important, that in neighborhood of an ordinary point, solution can be represented as a power series. So near x equals x0 ordinary point, we can represent solution as a power series. Y equals a0 plus a1 x minus x0 plus a2 x minus x0 square, and so on. So this is power series centered at x equals x0. Why do we need actually different centered power series? Why don't we center all of them at 0? Again, guys, normally we use power series to approximate actual solutions, right? And power series is infinite power series, and normally we cannot calculate the sum of infinite power series. Mostly they don't have formulas, so we calculate it numerically. To calculate the sum of power series numerically, we'll need to limit number of terms to some number like 1000 or 1 million. Closer to the point where we work, for example, we are working like our physics problem is working nearby the point x equals 2. Closer to the point we see it, the series centered, less terms we will need to count. So series is working best nearby the center, and it starts working worse and worse farther away from the center. Well, of course, depending on how many terms. If you have all infinitely many terms, it's going to be it's going to work, of course, everywhere. But normally we are going to limit ourselves, for example, to first two terms. Maybe it's going to work within a very short neighborhood of this x0. So that's why we need x0 actually. I'm going to start with an example, and I'm going to actually solve differential equation using this power series, okay? So let me scroll this up and do an example. I'm going to change my color, so example is going to be this way, okay? So example number one. Guys, in this section, examples are super long. Well, just because whenever we deal with serious lots of calculations. So I'll try to make it like as short as possible. So I'm considering a very simple equation, y second derivative plus y, oh, sorry, minus y actually. Eraser. Okay, minus y equals to 0, homogeneous equation. I'm going to set up initial conditions as y of 0 equals 1 and y prime of 0 equals 2. Well, again, just for example. So I'm going to consider a solution as a series solution. I'm going to look for y equals, let's consider solution at point x equals 0. This is a regular point for this equation, right? The coefficient is equal to 1 here, so actually all points are regular. So I'm going to write it down about, we're going to consider it about x equals 0. Well, it's going to make our life a little bit easier. It's not impossible to consider it about any point here. All points are regular, right? So I'm going to write down general form of the series. Sorry, not supposed to be parentheses. General form of the series is an xn n from 0 to infinity. So we are searching for a solution looking like this, right? To plug it into this equation, we'll need to know the second derivative. So I'm going to differentiate it once, first derivative. And for power series, very easy to differentiate it, just power function differentiated, right? So if we differentiate x to the power of n, we are going to have n here and x to the power of n minus 1. And n starts with 1 to infinity. The question is why it starts with 1. Well, the first term in this series is a0, right? a0 is just a constant. If you differentiate it, so 0 term is going to give us 0. So it's going to just disappear from the first derivative. So that's why I start n equals 1 under my series. Now, what is going to be the second derivative, which we actually need? Well, one more time, differentiate it, and we differentiate actually just the power function x to the power of n minus 1, right? So it's n minus 1, and that's going to be x to the power of n minus 2. Now, because the derivative of this function is going to give me another constant like a1, it's going to disappear when I differentiate it a second time. So I'm going to start actually with 2 here. I want to write down equal sign for me with 2 and again to infinity. Well, now I'm ready to substitute it into differential equation. What I'm going to do, guys, here I'm going to shift my index. I'm hoping that you did a review of section 5.1 where we deal with series and different theorems about series, which we were supposed to know already, but if you forgot, that review is going to be good to do. Okay, sorry, my formulas disappeared. So I'm going to shift my index back to 0. Why? Because when I plug it into my equation, this one as a solution, this one is a solution. If I plug it into the equation, my sigma here starts with 0. I want to have a similar sigma for second derivative. If I want to write down everything in sigmas, I want to have like similar sigmas. So here I'm going to shift the index, shift the index and move it to 0 back. So what it's going to give me? Well, normally, guys, we're supposed to say m equals n minus 2 and kind of go to the index m, because if you plug in like n equals 2 here, it's going to give you from 0 to like infinity now, and here n from here, from this little equation over here, n equals m plus 2. So I'm going to put actually here m plus 2, the index, right? And m plus 2 instead of n over here. And, well, if I subtract m plus 2 minus 1, I'm going to get m plus 1. And my index over here at x, instead of n minus 2, is going to become just m, because m is exactly n minus 2, right? Now, guys, I don't want to have a different numeration summation index here. Actually, for the sum, summation index is going to just like show like what numbers we are going to use. So you can name it as you like. It's not necessary to name it m. We can go back to n, and that's what I'm going to do. I'm going to go back to n. So, sorry. So it's going to be a n plus 2 and n plus 2 n plus 1. And guys, if you feel that you can skip intermediate steps here and just shift the index without them, I'm going to be fine with it. That's not necessary actually to show all the steps. I'm showing it once for everyone to kind of, you know, see how it works. So this is x actually. When I'm touching my screen, my pen does not work. Okay, now I'm going to plug in this expression and this expression into equation. So my second derivative is going to be a n plus 2 n plus 2 n plus 1 xn minus, and my function is a n x to the power of n, and n goes from 0 to infinity here, and here n goes from 0 to infinity equals to 0. So let me scroll it up a little bit. Now, guys, what I have here, I can unify these two sigmas into one. And like, because they are like same index and start with same number, right? And under one sigma, I can take x to the power of n outside of parentheses. So what I'm going to have in parentheses, it's a n plus 2, n plus 2, n plus 1 minus a n, and that's x to the power of n equals to 0. Sorry, my n is not very visible here. Now, what I'm going to use, if you did a review of section 5.1, you know that polynomial is polynomial. It's a function which has power functions, x to the power of n, equals to 0 for all x, only if the coefficients are exactly equal to 0. Otherwise, it's not going to be equal to 0. It's going to have some numbers somewhere. Well, I'm going to set up coefficients equals to 0, and I'm going to write down like a n plus 2, n plus 2, n plus 1, sorry, equals a n. I just moved this a n from the left side to the right side. Now I can solve for n plus 2, and I'm going to get n plus n, a n divided over n plus 2, n plus 1. Right? What we have is called a recurrence formula. It's called recurrence formula. So it's how do we find next term if you know the previous one. Now, guys, to show how the series is going to look, I'm actually going to calculate few first terms. So, for example, I'm going to set up n equals, sorry, I don't know why my pen is not working, I think because I'm touching the screen, n equals 0, and I'm going to get that a2, if I plug in 0 here, equals a0, and if I plug in 0 here, it's 2 and 1, and I'm going to do n equals 1, a3 equals a1, 3 by 2, n equals 2, a4 equals a2 divided over 4 by 3, right? But I do know a2 already, so I'm going to plug it in. That's a0, 2, sorry, well, I'm going to copy first 4, 3, and then 2 and 1. I can actually write down a0 over 4 factorial. And here I can write down a1 over 3 factorial, right? Well, 2 factorial 2 over here. I'm going to do like maybe 2 more to show you how the pattern is working. And 3 is going to give me 5, which is going to be A3 over 5, 4. And because we do know A3 already, I'm going to plug it in over here instead of A3 and get A1 over 5, 4, and 3 factorial, which is going to give me 5 factorial. Well, I don't know, maybe one more term. And we are going to write down everything in a series. So n for A6. Sometimes I click on the eraser and instead of writing down, it's erasing. A4 over 6, 5, and we do know A4 where it's A0 over 4 factorial, so it's A0 over 6, 5, 4 factorial, which is A0 over 6 factorial. Okay, I'm going to stop at this point and I'm going to start plugging in my coefficients into my series. Remember, guys, that A1, A2, A3, 4, and so on are coefficients of corresponding powers of x. For example, A0 is coefficient of x to the power of 0, which is like 1, right? And A1 is coefficient of x to the power of 1, and A2 coefficient of x to the power of 2. So I'm just going to write them down next to the series, next to the terms they have. So A0 plus A1x, I don't have anything about them, right, in these relations, plus, instead of A2, I'm going to write down A0 over 2 factorial. Instead of A3, oh sorry, I'm missing x squared actually, important. Instead of A3, I'm going to write down A1 over 3 factorial x cubed. 3 does not look like 3. Just kind of write down 3 one more time. And plus what we have, next one, A4, that's A0 over 4 factorial x to the power of 4 plus A1 over 5 factorial x to the power of 5 plus, last one, A0 over 6 factorial x to the power of 6, and there are going to be more terms. What I'm going to do, guys, I'm going to unify terms with A0 and terms with A1 separately. So first term with A0 is 1 from here, right? Plus x squared over 2 factorial plus x to the power of 4 over 4 factorial and plus x to the power of 6 over 6 factorial. And there are some other terms which I'm not writing down, right? A1 has x plus x cubed over 3 factorial plus x to the power over 5 over 5 factorial, and I did not calculate more, but I think it's going to be enough for a while. Now I'm going to scroll it up, and well, what I have actually, guys, well, it looks a little bit strange, but for us it's supposed to look like you know, a constant, some constant, multiplied by a solution. This series is a function, and we can call it y1. And this series is a function, and we call it y2. So we actually have y equals a constant multiplied by y1 and constant multiplied by y2. Those two are solutions. And these two solutions are linearly independent. How we can tell it? Well, you cannot express x squared from the powers of x or x cubed or x to the power of 5. Well, x squared, it's like a different polynomial. Remember that all these polynomials are linearly independent of each other. So some of them is going to be like linearly independent from another sum. So we have two linearly independent solutions, two constants. Now we just need to find constants using initial conditions, right? So my initial conditions is y of 0 equals 1. So I'm just going to plug in x equals 0 here. So x equals 0 is going to kill all this, right? 0, 0, 0, 0, 0. And going to give me a0. So my a0 equals 1. a0 equals 1. What is going to be my derivative. Well, first we'll need to calculate the derivative, right? So derivative of this expression, I'm going to just like write down like derivative of 1 is 0, right? And derivative of x squared is going to be 2x over 2, right? Factorial. And there are some other terms. And for the second term, we are going to have, a1, derivative of x is 1 plus some other derivatives. Well, I'll need to write down one more to show you why they are going to disappear. So it's going to be 3x squared over 3 factorial and some other derivatives. Now, guys, if you plug in x equals 0 into here, all the terms are going to have zeros in some powers, so it's going to just be equal to 0, right? Here, all these terms are going to have zeros, so the only one is going to work as a1. So a1 is supposed to be equal to 2, because the initial condition is equal to 2. So now we can write down our final solution as, well, we can put 1 instead of a0 here, just like formally, but it's not necessary actually. It's 1 plus x squared over 2 factorial plus more other terms, right? I don't want to copy the series again. And for the second solution, we have 2 and 1 plus, not 1, x, x plus x cube, over 3 factorial and other terms, right? And we do have like 2 solutions, and they are linearly independent, so we kind of solved everything. Now, it always makes sense to check our new method, how it kind of, related to the old ones, which we know. Equation which we were solving is very simple. So I'm just going to check our solution because using traditional method, right? Remember, equation was looking like this. Second derivative of y minus y equals 0, y of 0 equals 1, and y prime of 0 equals 2. Well, it's very easy to solve using characteristic equations. That's what? R squared minus 1 equals 0. So R equals plus minus 1, and solutions are C1 e to the power of x plus C2 e to the power of negative x. If you compare it to these 2 solutions, they don't look like this, right? Maybe after we find the constants, they're going to look like this. Let's do the constants. So y of 0 is going to be what? C1 plus C2. If you plug in 0 here and 0 here, it's 1 and 1. So we have C1 plus C2 equals 1. Y prime of 0. When we differentiate this, it's going to just stay, and that's still going to be 1. When we differentiate the second function, because it has minus, it's going to give us minus in front of C2 and equals to 2. If we solve it, for example, we add them. 2c1 equals 3, from where c1 equals 3 over 2. If we plug it c1 3 over 2 here, we subtract 1/2 and get c2, right? c2 is 1/2. That's 3 over 2 minus 1/2 equals to 1. It doesn't look like 1. Okay, now let's put them over here and write down our solution. Again, initial value problem. 3 over 2 e to the power of x plus, it's supposed to be minus actually, because we already calculated it's negative, minus 1 over 2 e to the power of negative x. Well, they definitely don't look like my series solutions. What I'm going to do, guys, I know that exponential function can be represented as a series, and I'm going to represent it as a series and simplify a little bit. Just want to make sure that my solution looks like this one, because 2 different methods solving same initial value problem supposed to give me same function. Remember, uniqueness theorem. So let's do it. So for exponential function, it's 3 over 2, and the first term is what? 1, and then x squared over 2 factorial, and then x cubed over 3 factorial, and then other terms, right? And minus 1 over 2. And actually this one is going to be very same, just because it's negative x is going to give me minuses for odd powers of x. So it's 1 minus x, but again plus x squared over 2 factorial and minus x cubed over 3 factorial and so on, right? I'm going to simplify it a little bit. So if I combine these first 2 terms, which don't have x, that's 3 over 2 minus 1 over 2 is going to give me 1. And then I'm going to combine second 2 terms. I'm going to combine 3 over 2x plus 1 over 2x is going to give me 2x, right? And next terms, 3 over 2 x squared over 2 factorial and minus 1 over 2 x squared over 2 factorial. So it's basically, again, x square over 2 factorial. And I'm going to do one more. So this one, cube, it's 3 over 2, and this one is minus minus plus 1 over 2. So it's going to be plus 2x cubed over 3 factorial. And there are going to be more terms. What I'm going to do, guys, I'm going to put terms with 1 up front. Okay, and terms with 2 kind of in parentheses. That's x plus x cubed over 3 factorial and some other terms. Do you see that now solutions are identical? The first set of numbers is 1 plus x squared over 2 factorial and so on. And the second set of numbers is the x plus x cubed over 3 factorial and multiplied by 2. Remember, uniqueness theorem tells that there is only one solution of initial value problem if the coefficients are continuous. But both solutions are going to produce two linearly independent solutions. Just you see that here solutions y1 and y2 were exponential functions, so like looking like this. They are not same with these two solutions. But we remember that we need only two linearly independent solutions to solve differential equation of second order, right? And they're not necessarily supposed to be same. You found another set of two independent solutions and they solve it. Finally, for the final answer for initial value problems, they're supposed to give you exactly the same answer, and that's what they do. But functions itself, like this one and this one, are different from this one and this one, and still are going to work and still going to give you same solution. Okay, now guys, in the next problem, I solved Airy's equation. I don't want to solve it on the board. It takes about a page of calculations for the coefficients, and it's just more practice. Can you just look through my written notes, which are attached to this section, and go over my written notes? In problem 2, I still keep working with sigma notation. If you don't like sigma notation, normally, guys, you can just work with powers of x. Just write down the sum. Let me just kind of say two words. It's not necessary to work with sigma notation like this, a n x to the power of n all the time. What you can do, you can write down a0 plus a1x plus a2x squared. It's just going to take a little bit longer than sigma notation, but you can deal with polynomials. Just remember there are many terms in them. And you can differentiate them, you can plug them into equations, and you can find relations between the terms. Exactly the same way you do with sigmas. Sometimes people don't like sigmas. I know that about like 40% of the class usually does not like working with sigmas. They are easier to work with polynomials. You can work with polynomials. Normally, we never need like all the coefficients, and normally it's going to be extremely hard to find general formula for coefficients. So usually I'm going to ask you to find like first two coefficients or first three coefficients in each solution. So you just kind of find this like first two, first three coefficients and put them back into the series, and I'm going to be happy about this. Okay, so I want you to read actually in my notes example 2 and example 3. I'm solving their two Airy's equations, and I'm going to write them down, but I'm not going to solve them. Example 2 is going to solve Airy's equation. I'm going to actually provide the graphs for Airy's functions, Airy's equation, and example 3 is going to solve the very same Airy's equation but about a different point. Well, these two examples are supposed to teach you how to deal with series better. So for example 2, I'm searching for a solution looking like this at point x equals 0. So x to the power of n. At example 2, I'm searching for a solution at point x equals 1, around point x equals 1, if we actually working nearby this point. And then solution is going to look like x minus 1. Please read examples. I'm explaining how to deal with different points if they appear as coefficients, okay? It's important to understand. And, well, again, if you don't like working with sigma, example 3 is going to teach you how to kind of do not work with sigma. I'm kind of keeping the sigmas until I just move 2 powers of x. Okay, and both are not going to be initial value problems, so I'm just looking for general solutions, and they're not going to look very nice, but they're going to teach you important kind of, skills of how to work with series. I don't want to make this lecture like super long. It's already about I don't know, it's already about 30 minutes long. Each of these 2 examples is going to take another 15 minutes, make it 1 hour. Okay, so what is going to be next? Section 5.3, right? I don't know if I prepare a video on 5.3 or not, because 5.3 I'll do a little bit more examples, plus I'm going to give some theory. Okay, for today's lecture, that's all. But again, I'm asking you to look at the notes because there are 2 more examples. I'm going to label in my notes, okay? Please solve at least 1 serious problem as a homework before you do the quiz, okay? And I'm going to put section 2 on the next quiz. So the quiz for Monday is going to be 6.4, where we learned how to solve equations with step functions. Plus, I'm going to ask you solve a question from 5.1 from review. Section 5.2 and section 5.3 are going to be on Tuesday's quiz. Okay, so you will have time to work a little bit more with series. And I cannot teach you the rest of chapter 5 because it's going to take me the rest of the class to teach everything, like what should we do with singular points and how do we kind of solve equations at singular points and consider actually Bessel's equation. It's just we don't have time. We still need to cover Fourier series. We still need to cover partial derivatives equations. And maybe if we do have time, we're supposed to cover also numerical methods. But I'm not sure that we are going to have time for all of this. Okay, thank you, and see you in my next lecture.